Okay, this afternoon, the first talk is we're happy to have Insung Park from Stony Brook University, and the topic is puncture-forgetting maps for measured applications of foliations.
Okay, thank you for inviting me and thank you for the introduction. So this talk is based on joint work with Jeremy Khan, who was my first postdoc mentor when I was working in Brown. So this project was motivated by some problem in complex dynamics, the dynamics of postcritically defined rational maps. But this content develops some more general theories in topology and geometry of surfaces. And we believe it has some more interesting applications. So please let me know if you have any ideas about it. So for that full map, so we consider closed surface with punctures. Sometimes we consider it as a marked points instead of punctures. So forgetting marked points is equivalent to some filling punctures. So for Riemann surfaces, filling puncture is simply defined by the removable singularity theorem. We can just literally add one more point in the puncture disk. But if you consider hyperbolic structure, then this puncture looks like cos. It has infinite geometry. So filling puncture is one-point compactification of corresponding cos, and it changed the geometry globally. And some ideas of forgetting punctures were understood in some context. For example, there's a Berman exact sequences. So if you consider mapping class group of n+1 puncture surface, and then it can be understood as a mapping class of the puncture field surface, but it has some infinite kernel, which is the fundamental group of puncture field surface, where this star is the extra puncture we forget from n+1 puncture surface. And this map injection is defined by push map. And in Teichner space there's a holomorphic surjection from the Teichner space of n+1 puncture surface to n puncture surface. And the fiber is tautological universal cover of the base surface. So if X is the n+1 n puncture surface, then the fiber is the universal cover of this n puncture surface. So we consider simple closed curves. By that I mean the embedded circle in the puncture surface. And we say that it's trivial if it bounds a disk, and it's peripheral if it bounds a once puncture disk, and call it essential otherwise. So here is some example of forgetful maps for simple closed curves. So this gamma 1 and gamma 2 and gamma 3 are three different simple closed curve in once punctured genus 2 surface. But if you fill this puncture, then they are all homotopic to each other. So we say that those three curves are pre-homotopic, in the sense that they are homotopic to each other in the puncture field surface. So you can easily generate infinitely many homotopically different pre-homotopic classes of simple closed curves. And if you have more than one punctures, if your simple closed curve bounds twice punctured disk, one of them is a puncture we forget, then after filling that puncture, your essential simple closed curve becomes peripheral. So we call such a curve pre-peripheral. And we also consider measure foliation, which is the foliation of surface which have finitely many singularities. such that near the singularity, the foliation looks like one of these pictures. So it may have one-pronged or three or four-pronged singularities. And the important thing is this one-pronged singularity is allowed only at the marked point. So this three-pronged or four-pronged singularity, this singular point may not be this one of n marked point, but this point, one-pronged singularity has to be one of this marked point. And transverse measure means we can measure the length, the length of arc, like how much it transfers to this measure foliation. And this, so important observation, this theory of measure foliation is that the measure foliation can be seen as a limit of simple closed curve. So if we consider square torus, and suppose that the sequence of rational numbers Pn over Qn converges to an irrational number alpha. And if you draw the picture of a simple closed curve defined by Pn over Qn, then you get some, the union of these segments forms a simple closed curve of the torus. And if your slope, rational slope, converges to irrational number, then your picture is getting more complicated and it fills the entire surface. And you can see that it converges to this foliation on the entire surface. So this is an important diagram proved by Thurston. So let SC be the set of homotopy classes of essential simple closed curves, and MF be the set of equivalent classes of measured foliation. So the simple closed curve, it can be seen as the measured foliation. You can just foliate the entire surface by using the the simple closed curves, which is homotopy to the given simple closed curve. Then you can fill the entire surface with parallel simple closed curve. So we have an embedding, and measure foliation embeds into the dual space of simple closed curve. So by that I mean this measure foliation is mapped to the functional such that it sends its homotopy class of simple closed curves to the intersection number with given foliation. So it embeds, and even if you projectivize this functional space, it's still the projective measure foliation still embeds in the projectivized dual space. So this is a picture how Thurston compactified the Teichner space. So he also embeds a Teichner space of S into this dual space by, if you have X, you consider it as a hyperbolic structure on the surface, then it sends, you have a hyperbolic length function, sends its homotopy class to the hyperbolic length of gamma with respect to this hyperbolic structure. And it embeds, and it also embeds to the projectivized dual space. So the schematic picture here is, if you consider this dual space, and the measure foliation looks like a cone. The Teichner space looks like a hyperboloid. So if you projectivize And you can see the disk here inside, and the measure foliation compactifies this disk shape with the sphere. This is PMF is homomorphic to the sphere. And the set of simple closed curves they form a discrete subset in this cone. But if you projectivize, then they form a dense subset in the sphere. So we call this is third sense compactification. Algebra space. Okay. Any questions so far? So yeah, let us discuss forgetting punctures from measure foliations. So let star be the puncture we want to forget. Then there are some kind of easy case where we can forget this puncture relatively trivially. So yeah, so first suppose this case. So if the star is two-pronged singularity, then we can literally just forget this mark point without any extra work. And if it has three or more prongs, then we can also forget this marked point because these 3 or 4 more prongs are allowed at non-marked point. So we are good. But in some cases, it's a one-prong singularity, but its leaf contains other singular points that we cannot immediately forget, but this equivalence class of measure foliation allows some topological deformation. So we can collapse these line segments, and we get to this first easy case. So we can forget the puncture. Another case is if the singular leaf is a line segment, then around this data connection, you have the closed leads, which are consist of parallel simple closed curves. Then you can take the maximal saturated neighborhood of it, and we forget this entire yellow disk. And yeah, in this way, we can also relatively easily forget this extra puncture. So the difficult and generic case is the following. So suppose that the star is one-prong singularity, and the leaf containing it is homomorphic to the half-infinite line. And suppose that the leaf is dense. So this is generic condition of measure foliation. So you can immediately observe that it's not very easy to forget this extra puncture and define the measure foliation on the puncture field surface. So yeah, have any wisdom? Okay, so we cannot forget immediately. So we forget the puncture kind of implicit way. Before talking about it, let's discuss the discontinuity of this forgetting process. So suppose alpha is a pre-peripheral curve and beta is an essential curve like this. If you twist alpha along beta many times, then the sequence of twisted curve converges to beta in the projected measure foliation. But all these curves are pre-peripheral. So if you forget the star, then it gives you some, you get peripheral curve, which we denote by 0. but the limit is beta, and beta survives even after we fill the puncture. So yeah, this shows some discontinuity phenomenon in the puncture filling process. So it's difficult to forget puncture from this measure, the picture of measure foliation, but there's a kind of canonical way to forget puncture in the level of the dual space of simple closed curves. So consider that the puncture forgetting is well defined the set of simple closed curves, and we should add one more symbol to denote the peripheral simple closed curve, because for there exists some essential simple closed curve that becomes peripheral in the puncture filled surface. So we need this extra symbol. And this map is infinite to 1. There are infinitely many different pre-homotopic simple closed curves. So we define this forgetting map, the duals, the functionals of simple closed curve as follows. So we send f to phi where phi gives the infimum value over these pre-homotopic simple closed curves. So gamma is the homotopic, gamma is a simple closed curve on the puncture filled surface. Then there are infinitely many different homotopic classes of simple closed curves in n+1 punctured surface. And we evaluate the value of f at about, these infinitely many simple closed curves, and we take the infimum. So we can define these forgetful maps in the level of functionals on the simple closed curves. So this phi of f is a functional. And we can ask whether this functional is realized by the intersection number of some measured foliation on the puncture filled surface. And it defines the forgetful maps for measured foliations. So we have realization problem. And the main theorem is that, it's realized. So if I flip the logic here, so there is an upper semi-continuous map for measure foliation of n+1 puncture surface to n puncture surface. We satisfy this definition of forgetting map for functionals. And this set of measure foliation contains 0 for the convention. And there exists a dense G delta set that is intersection of open dense, countable intersection of open dense subsets, such that every element in this G delta dense subset, its forgetful map image is 0. And this set V contains all the stable and unstable measures foliation of point pushing map Surano of mapping class. There's a nice theorem by Kra. This is the first map, injection map in the Berman exact sequence. So this point pushing image is Suranos of mapping class if and only if this loop, the fundamental group, is filling in the sense that it intersects every simple closed curves. So for those invariant foliation of point pushing Suranos of mapping classes, their forgetful map image vanishes. And let us consider the forgetful maps on the Teichner spaces. So you have X here, which is in the Teichner space of Gn, in the Teichner space of Gn+1, and It's denoted by pi. Then the pi inverse of x is a subset, the fiber of this surjection, which is isomorphic to D, which is isomorphic, tautologically isomorphic to the universal cover of X. So you can, and there's a measure foliation, it's Gn+1, where we have F, and we have puncture forgetful image, phi of F, and measure foliation of SGN. So we can consider the extremal length of this puncture field measure foliation with respect to X. And we show that this extremal length is equal to the infimum of extremal length of the original measure foliation over this fiber. Fiber is forgetful maps of the Teichmüller space. And we also showed that, so this surjection map pi is holomorphic. That implies the Teichmüller distance contracts under the pi. So this, the second inequality is quite trivial. Well, it follows from the fact that the Teichmüller metric is a Kobayashi metric. But we also have a lower bounds by a uniform distortion C. So that means if you generate a Teichmüller distance upstairs, a Teichmüller geodesic upstairs, generated by this measure foliation. By that I mean the Teichmüller geodesic is generated by quadratic differential at the reference point, and the quadratic differential, the horizontal measure foliation, well, it determined the horizontal measure foliation. So the geodesic generated by F means it generated by measure quadratic differential horizontal measure foliation is F. So if phi of F is non-zero, then you have a uniformly bounded contraction along this geodesic. So this pi of x t is not a geodesic, but it's 1C, 1,C quasi-geodesic. So, okay, this is what the properties that we found out about this phi of F. Okay, any questions? So we had some trivial example where we can trivially forget the puncture. For those cases, it's non-zero, obviously. Yeah. For simple closed curve with pre-essential, it's also non-zero. But yeah, but we don't know any other examples. Okay, so then most important question is why we should care about it. So as I mentioned, we were motivated by a conjecture raised by Kevin Pilgrim. So consider a post-critically finite rational map. By that, I mean every critical point is eventually periodic. So Pilgrim conjectured that we should exclude flexible lattice map as usual. Then there is a finite subset of the set of simple closed curve such that for any simple closed curve, under some large backward iteration, all the essential components with backward images are contained in this uniformly fixed finite subset of simple closed curve. So yeah, let us discuss what that means with some explicit examples. So this is a rabbit polynomial which has two critical points, 0 and infinity. Infinity is a critical fixed point. 0 is mapped to C, and C is mapped to C squared plus C, and C squared plus C mapped back to 0. So we form a critical 3 cycle, and its preimages has 2 extra points. This set of 3 simple closed curves form a attractor here. So let's see. So if you start from this green curve on the left, consider its backward image, then you get the simple closed curve. It contains 3 mark point preimages, but these 2 points are extra points. So if you fill these 2 extra points, then this curve in the middle is homotopic to the curve on the right, the original punctured sphere. So here you have pullback process and you forget extra puncture process followed. And if you start from this curve, the left, its preimage has 2 components, but this component will be trivial if we fill these 2 extra punctures. Then we get the curve on the right. The next, this curve on the left, its preimage has a single component, and to fill the puncture, then it back to the initial simple closed curve. So it forms a 3 cycle in the dynamics on the simple closed curve. Let's start with a more complicated simple closed curve. So let's consider the simple closed curve is the boundary of the thick arc, or you can just consider the dynamics of this arc. So its preimage has 2 components. If you fill these 2 extra points, then we only have 1 non-trivial component. And this 1 trivial component, the preimage is S-shaped, and fill these 2 extra points, then you get this arc and this arc. The preimage is Z-shaped. Forget these 2 extra points, then you get this arc. And this arc, the preimage has 2 components, but if you fill these 2 punctures, then you get 2 trivial or peripheral curves at the end. So what this conjecture really means is the following. So homotopic classes of simple closed curves in the Riemann sphere marked at the postcritical set are simplified under the backward iterate. So there are many partial results, mostly about the case when the size of postcritical set is 4. Misha Lushanka showed it for critically fixed rational maps, and Nikita, together with Sarah Koch and Kevin Pilgrim, proved this conjecture under the assumption that the Version endomorphism of mapping class group induced from the moduli correspondence is contracting in the sense of Nekrashevich. So, and recently Bartholdi, Duque, and Pilgrim established the conjecture when the size of postcritical set is 4. So, okay, so let us formulate this conjecture in a different way. So recall that the postcritical set is F invariant such that the preimage contains PF and contains more extra points. And this finite curve attractor conjecture is equivalent to that if you consider the dynamics on the set of multi-curves in the punctured sphere, then this dynamics has a finite set of attractor. Wherever you start, it eventually get into some finite set in the simple closed curve. And this dynamics is obtained by the composition of 2 maps. One is the pullback map. So every multi-curve in the sphere punctured at PF, if you take a pre-image, then you have a well-defined multi-curve on the sphere punctured at F inverse of PF. So there's nothing wrong in this process. You can just take a pre-image. Then we forget or we fill the extra puncture, the difference of the F inverse of PF and PF. Then it's easy to consider the homotopy class of curves in the puncture field surface. So it defines then the point is we have the same marked points at the end. So we can iterate this process and define the dynamics on the same set. The point is this multi-curve, set of multi-curve embeds in the set of measure foliation. So we want to do the same thing for measure foliation. So this pullback process is good. It's easy to pull back the measure foliation under covering. But the second process, forgetful map, was not defined. So that's why we developed this theory of forgetful maps for measure foliation, so that we extend the dynamics of the multi-curves to the dynamics of the measure foliation. And the nice thing to do so is the following. The PMF, project measure foliation, is homeomorphic to sphere, so it's compact. And you can say some more nice things if we do some dynamics on the compact set. We'll see later. And some relevant context is the famous Thurston's pullback map is defined on the level of Teichner space. This is also composition of the pullback of the complex structure and filling the puncture process, forgetful maps on the Teichner space. So this kind of see this the boundary, Thurston boundary behavior of the Thurston pullback map. I have to mention that, yeah, the Thurston pullback map continuously extends to the augmented Teichner space proven by Nikita. And augmented Teichner space is not a compactification, but it's a completion with respect to the Bayes-Peterson metric. So there are two obstructions to get the finite curve attractors. So if we assume that curve attractor is infinite, then we get to one of these two cases. First one is there's a wandering sequence of simple closed curves. So gamma 1 may have many pre-images, but let's say gamma 1 is one of them, and gamma 1 has many pre-images, and let's say gamma 2 is one of them, so that we may have, and this process may continue forever, then we get a backward wandering sequence of simple closed curve, which obstructs the existence of finite attractors. Another obstruction is there may be infinitely many cycles, different cycles in this backward process. So these are the only two obstructions to have finite curve attractors. And the important thing is in both cases, you have some infinite sequence of simple closed curve. And if you compactify the space of simple closed curve, then you can get a limit of the infinite sequence of simple closed curve. So that's why we want to do everything in the space of PMF. So suppose, so this is some partial results on the curve attractor conjecture we obtained. So F is PCF rational map, it's not a flexible lattice map. And suppose that there's a wandering sequence of simple closed curves. And we consider the Birkhoff average of the direct measures that these curves on the PMF, which is homeomorphic to the sphere. So you have an infinite sequence in the space of probability measures on a compact set. So it always has Wickstar limit. So we want to obtain the contradiction by using this Wickstar limit. And what we could show is that this weak star limit mu of this Birkhoff average is supported in the set of non-recurrent measured foliation, which is a kind of non-generic subset of measured foliations. So there's so in the set of measured foliation, the most famous measure there is the Thurston measure, which is kind of Lübeck measure. And with respect to Thurston measure, the set of recurrent measured foliation has full measure, but this our Vixar limit has zero measure on this set. So you can say that these two measures are singular. So our strategy to attack this conjecture is following. So we have shown that this Vixar limit mu is supported in the kind of singular measures, measure foliations. And we wanna upgrade this statements to that this mu is actually supported in the weighted F-invariant multi-curves. So multi-curves are some examples of non-recurrent measure foliation, but if you have more than 4 punctures, you have non-recurrent measure foliation that are not multi-curves. But if we have this property that mu is supported in F-invariant multi-curves, then it's known that this this pullback map enjoys some repelling property near F-invariant multi-curves. And if you consider a dynamical system and have repelling fixed point, then the repelling fixed point repels some points nearby. So you can easily imagine that the Birkhoff average of for the orbit is difficult. It's difficult that for the orbit is accumulated to the repelling fixed point. So that is the idea that we expect to get a contradiction from this wandering sequence of simple closed curve. And the similar thing happens for the second kind of obstruction. And as I mentioned that when there are only 4 post-curve points, every non-recurrent measure foliation is a single curve. So we can prove until 2, but we couldn't finish our proof. Well, we couldn't solve the third step. And Bartholdi, Duco, and Pilgrim proved the conjecture for this case with completely different perspectives. Okay, so this is our motivation and our vision to use the forgetful maps for measure foliation to make a progress in this problem. Okay, any questions? So, but it's generally difficult to upgrade the 0 to 1. But there's one sufficient condition, well, sufficient statements that, so we can ask whether phi of f is 0 for every star generic minimal measured foliation, because it's very difficult to forget the puncture. And we established, well, we showed that phi of f is 0 in the G delta dense subset of measured foliation. So it's the reasonable question. And Jeremy and I really wanted to answer this question, but we couldn't, and this bothered me for the past several years, and still don't have any answer. So we are half and half. So I'm like 60 to 40 to the affirmative answer, but Jeremy is opposite. He's more leaning to the negative answer to this question. So maybe it's bad, yeah. But anyway, yeah. So let me tell some underlying idea of this question. So the phi of f, it's a functional, is defined as an infinite intersection number with the foliation over this pre-homotopic classes of simple closed curves. So let's start with gamma 0. And this is a foliation. And this is a single trajectory. Then this first heating, the neighborhood first heating always looks like this. You can find the saturated neighborhood of these arcs. Then once you have this picture, then you can change gamma 0 to gamma 1. Then gamma 0 and gamma 1 are pre-homotopic. They are homotopic in the puncture field surface. But you can see that the transverse measure strictly decreased by this amount. So you can continue this process. So we change gamma 0 to gamma 1, and you draw more foliations, extend a single trajectory, and consider a second heating point. Then you repeat the same deformation to get gamma 2. And yeah, and you repeat this process along a single trajectory. Then you have a sequence of pre-homotopic simple closed curve. They are all homotopic to each other in the puncture field surface. And in each step, you can strictly decrease the intersection number. And this decrement of intersection number is exactly the same as the intersection, well, the length of this line segment that we forget. So eventually the leftover is the intersection number of the foliation with the original simple closed curve minus the union of these open intervals. And since we assume that the foliation is minimal, the intersection of this single trajectory with the gamma 0 is then subset of gamma 0. So the union of this open subset is dense in gamma 0. So the leftover is the intersection number of f with some contour subset of gamma 0. But we don't know whether this intersection number, the measure on the contour set, is 0 or positive number. So this contour set is kind of shadow memory in this forgetting process. And this question is related to whether the shadow memory has 0 measure or not. So this is another perspective of this question. So for a measure foliation f, this phi of f is 0 if and only if you can consider the point pushing action on the set of measure foliation. Then you can take the orbit closure of point pushing actions. And the phi of f is 0 if and only if this orbit closure contains 0. And some relevant context is the Linden-Strauss and Mirzakhani's classification of mapping class group orbit closures in the set of measure foliation. So according to their classification, if f is minimal, then the orbit closure of this full mapping class group is the whole set. So the orbit is dense. And we are not interested in the whole orbit, but we are only interested in the point pushing orbit closure. And we are interested in whether 0 is contained in the closure or not. So for the rest of 5 minutes, let me tell you some ideas in the proof. It's interestingly related to some cat-zero cube complex and where the point pushing acts co-compactly. Colors. So fix zeta, which is the homotopic class of simple closed curves in the puncture field surface. And F is a star generic major foliation. And recall that we have a well-defined forgetting map at the level of simple closed curve, which is infinite to 1. So Canford, Leininger, and Schleimer prove that, so the inverse of, so zeta lives here, and the inverse of zeta is the infinite subset of simple closed curves in the n+1 puncture surface. Then you can consider the subgraph of curve complex there generated by those simple closed curves, which are pre-homotopic to each other. And they show that it's a connected tree. And the key property is the following. So pick any simple closed curve gamma, which is homotopic to zeta in the puncture field surface. And if you move from this vertex gamma to adjacent vertex in this tree complex, and it always, well, there exists unique adjacent vertex for which the intersection number strictly decrease, but if you pick any other adjacent vertex, then the intersection number strictly increase. So the picture is the X zeta is locally infinite tree. It has only one edge for which the intersection number with F strictly decrease. So we can orient each edge toward the direction that the intersection number with F strictly decreases. Then it has only one outgoing edge. So each vertex has only one outgoing edge. Then if you pick any directed path in this graph, this tree, and if you measure the intersection number with F along this directed path, then it will converge to the infimal intersection number with this major foliation. So this is how we obtain this infimal intersection number by using this combinatorics. But to obtain the major foliation, we need to reduce the intersection number of not only one simple closed curve, but we reduce the intersection number of a set of simple closed curve, which determines major foliation. So by Thurston's 9G-9 theorem, you can find a finite many simple closed curve for which the intersection number uniquely determine the major foliation. Then the tree in the simple closed curve now generalized to some cat zero cube complex, which is whose vertices are pre-homotopic multi-curves. And we orient each edge in this cube complex in a similar way. Then interestingly, this orientation uniquely determines some roller boundary of cube complex. And we have that this point pushing mapping class action acts on this complex compactly, so we can approximate this infinite directed path by an orbit of infinite sequence of point pushing mapping class. Then the inverse sequence of this point pushing mapping class of this foliation F converges to some major foliation G, and we can show that this G is star non-generic. So we can forget this star in a trivial way from G, and we can define phi of F by using this G, then this satisfy the desired properties. Okay, that's all.